Hi, I'm Laura Iacconi. I'm a PhD student at the Institute of Cosmology and Gravitation in Portsmouth. And today I'd like to talk with you about some work that I've been doing with my supervisors, David Wans, Hushar Asadullah, and Matteo Fasiello. In particular, we have been exploring ultra-high frequency gravitational waves from alpha-attractor models of inflation. And the work that I'm presenting today is based on a paper that will soon appear on the archive. So watch out for that. So let's start from the beginning. Cosmological inflation is a period of accelerated expansion in the early universe, and it has been initially proposed in order to solve the main problems related to Big Bang cosmology. So a good way of keeping track of the expansion of the universe is by means of the scale factor A. And during inflation, the scale factor is an exponential function of n, where n is the number of e-folds of inflation. So if you have 60 e-folds of inflation, it means that the A increases by a factor of e to the 60, okay? So this is inflation. N in particular, so is given, let's say more formally, as an integral over time of the Hubble rate during inflation. On top of the expanding background, one needs to consider also perturbations. And in particular, today I want to focus on the curvature perturbation zeta, which is the main source of the temperature fluctuations of the cosmic microwave background. A very good way of describing zeta is by means of the 2-point statistics of it. And this goes by the name of the scalar power spectrum, P zeta of K, where K is the scale, usually expressed in inverse megaparsecs. On large scales, it is a good thing, is a good approximation to model the power spectrum as a simple power law, where AS is the amplitude, the power law is centered at 0.05 inverse megaparsec, which is the usual CMB scale, and the tilt of the power law, which tells you, how the power spectrum changes depending on the scale, is given by NS minus 1. From measurements of the cosmic microwave background anisotropies, it is possible to constrain these parameters. And in particular here, I'm reporting the up-to-date measurements from the latest Planck collaboration release. So alpha-attractor models are a particularly compelling model to describe inflation. So amongst all the possibilities, we think it's really good to look at alpha-attractors. First of all, because they are in accordance with the current CMB observations. And then also because they provide universal predictions for the CMB observables. So let me explain this a little bit better. The CMB observables within alpha-attractor models don't really depend on details of the potential, and they can be given by general expressions which depend on the number of e-folds elapsed between the CMB crossing, so when the CMB scale crossed the horizon to the end of inflation. And this is NCMB. So here you can see, for example, the expression for the tilt, NS, which is a simple expression of NCMB, and does not depend on details of the inflaton potential. Also, alpha-attractor models can be embedded in supergravity theories. And here at the bottom, I'm reporting just a couple of the early works by Kalosh and Linde to present alpha-attractor models. But a lot of people have been working on them. So this is definitely not an exhausting list. Alpha-attractor models are naturally formulated in terms of two fields, an angular field phi and a radial field phi and an angular field theta that live on a field space with an hyperbolic geometry. Usually during inflation, it is possible to stabilize the angular field theta. And so usually you can describe inflation with an effective single field version of alpha-attractors, and you can see here the Lagrangian for it. So phi is the inflaton, is the field that drives inflation, and its potential is a function, can be any function of the hyperbolic tangent of phi over square root of 6 alpha. So it is possible to consider different functions, as I said before, to build up the inflaton potential. And in particular, we wanted to focus on function that can allow for the presence of an inflection point. And this has been done also in the literature in this reference that you can see here. So we have parameterized the inflaton potential in a very clear way. So this is a cubic function, the square of a cubic function of the hyperbolic tangent of phi over square root of 6 alpha, and each coefficient have a very clear interpretation. So the potential is, in other words, the potential is parameterized by the curvature of the fields of the hyperbolic field space, which is connected with alpha, the position of the inflection point, which is R inflection, and the first derivative of the potential at the inflection point, which is related by the parameter psi. When psi is equal 0, then the inflection point is stationary. If psi is different from 0, then it is non-stationary. And here in this plot, I'm representing the potential profile against phi values for a non-stationary inflection point potential. So once you are given an inflaton potential, you can numerically evaluate what is the power spectrum predicted by that specific model. And this is what we have done. So I've taken the potential that I've just shown you in the previous slide and numerically evaluated the power spectrum of the curvature perturbation, which is plotted here in yellow against K, the scale, in inverse megaparsec, or alternatively against the frequency expressed in Hertz. And what happens is that on large scale, the power spectrum is very well described by a simple power law. But when you go on small scales or high frequencies, the dynamics at the inflection point enhances the power spectrum. In particular, the mechanism that is beyond this, that is causing the enhancement of the power spectrum, is an ultra slow roll phase. When the curvature perturbation is enhanced sufficiently, it can lead to primordial black holes production. And in general, any enhancement of the curvature perturbation leads to second order gravitational waves, which might be detected or not. In particular, the second order gravitational waves can be described by the omega GW, so the energy density stored in these second order gravitational waves, which is given by a rather complicated integral of the square of the power spectrum. We have found that the universal predictions still hold. They need just to be modified. And by this, I mean that instead of having expressions that depend on n CMB, so the number of e-folds elapsed between CMB and the end of inflation, now what really matters is the position of the peak. And so the universal prediction hold under under a simple modification. You just need to replace n CMB with n peak, where n peak is the number of e-folds elapsed between the CMB scale and the peak scale. And here I'm showing you two power spectra coming from two different potentials. And you can see that on large scales, they can be very well approximated by just power laws. And when you move on towards higher frequencies, they exhibit two peaks. And you can see that depending on the position of the peak, the tilt on large scales changes. In particular, the magenta line is not compatible with the CMB measurement of the tilt, while the yellow line produces a tilt that is compatible with the current CMB measurements. So what we have found is that in order for the models to be compatible with the CMB, the phenomenology is constrained, and in particular, the scale of the peak is constrained to be a very high frequencies. In particular, here you can see the correct expression. And the consequence of this is that the primordial black holes produced are evaporated by today, so they cannot constitute a candidate for dark matter, and that the second order gravitational waves they peak at ultra high frequencies. So here you can see a plot displaying the energy density in gravitational waves, plot against the K, the scale in inverse megaparsec, or alternatively the frequency in hertz, and the signal is the yellow line. So you can see that for a configuration that is not in tension and is compatible with the CMB measurement, the peak of the second order gravitational waves is at ultra high frequencies, beyond the reach of current and planned ground and space gravitational waves observatories. What we have done then is to extend in a multi-field setup the inflection point potential. And as I told you at the beginning, this is quite natural for alpha-attractor models because they are indeed initially formulated in terms of two fields, phi and theta, that live on a hyperbolic field space. What happens is that when you are in a multi-field setup with a hyperbolic geometry in field space, geometrical effects and turning trajectories can lead to a very rich phenomenology. And this has been investigated a lot recently. And you can see here a list of some works in this direction, but this list is obviously not exhaustive, it's not complete. So here I'm showing you some trajectories that correspond to different initial conditions for the angular field, plotted on top of the multi-field potential that we have derived. And you can see that these colored lines display a very rich behavior, and in particular, the trajectories are turning in field space. What happens is that given a certain potential, you can numerically evaluate the scalar power spectrum again. And we have that on large scales, again, the power spectrum can be well approximated by a power law, but on small scales and high frequencies, the power spectrum does exhibit a peak, so a large enhancement. The peak in this case, though, is produced by multi-field effects. So is not produced by the same mechanism that was at place in the single field scenario. What is common between the single field and the multi-field scenarios is that the compatibility with the CMB locates the peak in the power spectrum at ultra high frequencies. So again, these modified universal predictions, we have found them to be robust against multi-field effects. And again, for the models to be compatible with the CMB, they need to exhibit a peak at ultra high frequencies. With an enhanced scalar power spectrum, you have second order gravitational waves production. And here you can see the signal in green that I have numerically evaluated for the potential shown in the slide before. And so the amplitude of the signal depends in this case on alpha, so on the curvature of the hyperbolic field space, and on the initial condition on the angular field. So the amplitude really changes depending on the potential that you consider, but what is universal about these models is that in order to be compatible with the CMB measurements, the frequency of the peak has to be at ultra high values. So again, the frequency of the peak of the scalar power spectrum and the second order gravitational waves is constrained by the compatibility with the large scale measurements. So to conclude, we have discussed inflection point alpha-attractor models, both in single field and multi-field setup. And we have found that the scalar power spectrum can be enhanced at high frequencies. An enhancement of the scalar fluctuations naturally leads to the production of second order gravitational waves. And we have found that in order for the models to be compatible with the CMB measurement, in particular the measurement of the tilt of the power spectrum, well, the peak has to be located at ultra high frequencies. So here I'm leaving on the screen the peak, the energy density in gravitational wave plotted against the scale for a single field configuration and for a two field configuration. And you can see that these two signals are different from each other, but they share a common feature, which is that they are peaked at ultra high frequencies for models that are compatible with the CMB measurements. So I hope that this talk gives you a theoretical motivation to look for gravitational wave signals at ultra high frequencies. And I would thank you for your attention, and I'm really looking forward to answer to your questions during the live session.